So hi there, I am Anuj Kumar. I'm working as a Prime Minister Research Fellow at IIT Roorkee, and this is the assignment 4 of this course, that is trace and ultra trace analysis of metals using AAS. Okay, so let me confirm first whether it is okay. Right. So the first question of this particular assignment, this is assignment 4. That is the hollow cathode lamp used for the determination of element uh, must not contain the same element, must contain the same element, must not contain any other element, or may not contain the element. You have to choose the right options for this. Okay, so I'll wait for 1 or 2 minutes. After that, I'll explain the whole theory of this HCl, hollow cathode lamp. So, you know that there is a basic requirement for the AAS measurements, that is the HCl hollow cathode lamp contain the same, it should contain the same element that has to be analyzed. Okay, so this option will be the right answer. So here you can see the typical structure of this hollow cathode lamps. So there is a cathode, okay, and there is one anode. Okay, so this is the phenomena that basically taking place there. So what happens first? There is a filled filled gas here that is basically inert. You can say the argon gas is suppose that. So what happens if I apply the electric voltage? So the filled gas uh, dissociated or ionized, right? And that connects with this cathode that is basically made of the same element that you have to analyze. After that, what it does, it basically excite that metal, okay, and like this metal get excited to the higher state, and when it returns to the ground state, it emits the particular radiation of the wavelength, a particular wavelength, right? So this the same phenomena is shown here. So, and this one is the basic picture of the hollow cathode lamp. Here, this is the anode and this is the cathode, right? You can also use the cathode made of the alloys also, because if you have to analyze the you have to do the multi-element analysis. You can choose this cathode of any alloy, right? So here, this gas is neon. So first, what happens? This neon plus get disclosed here, and after that, M is converted to this excited state, and after that, when it returns to its ground state, it emits this particular radiations. Okay, and the same theory is written here. The source for atomic absorption is a hollow cathode lamp that consists of a cathode and anode enclosed within a glass tube filled with a low pressure of an inert gas such as neon or argon. Okay, so applying a potential across the electrodes ionize the filler gas, right? The positively charged gas ions collide with the negatively charged cathode, sputtering atoms from the cathode surface. Okay, this phenomena is called sputtering. Some of the sputtered atoms are in excited state and emit radiation characteristic of the metal from which the cathode is manufactured. So, by fashioning the cathode from the metallic analyte, a hollow cathode lamp provides emission lines that correspond to the analyte's absorption spectrum. Right? So, basically, this is the source of radiation. for that particular element which has to be analyzed, right? So HCl must contain the same element that you have to analyze. Clear? Okay. So let me go to the next one, that is that is about electrode less discharge lamp. Okay. So you are asked about the ideality for this ELD lamp, electrode less discharge. Okay, so you have to tell about the elements whose resonance line are below 200 nanometer, or it can be used for elements whose resonance lines are above 200 nanometers or 400 nanometers, or there is another option that is none of these, right? So in the last lecture, I have also discussed about two less than 200 nanometer. There are many interfering agents like oxygen, nitrogen, and moisture, etc. So for that particular reason, ELD lamp is ideal, right? Okay. So let me first discuss what is the this EDL. Basically, this electrode less, as its name indicates, it has no electrode, right? So there is a RF coil here. What you have to do, you have to just put the salt of that particular metal, right, into a bulb. Okay, you can see the elaborated version here. So there is a ceramic holder and a lamp in it is. So in this cavity, you have to put the metal salt, right? So a typical lamp is constructed from a sealed quartz tube. This is a quartz tube and containing a few torr of inert gas such as argon and a small quantity of metal or its salt, whose spectrum it is of interest, right? So the lamp contains no electrodes, but instead this RF coil energized, right? Instead is energized by an intense field of radio frequency or microwave radiation. Okay, you can use the RF or microwave radiation, right? So ionization of the argon occurs to give ions that is accelerated by high frequency component of the field until they gain sufficient energy to excite the atom. Okay, you can correlate this phenomena with this phenomena also, right? First, here, what is a specific property here? The RF coil, or the, you can say, the radio frequency convert the gas to ions, right? And they follow the same phenomena. So EDL are available commercially for 15 or more elements. So it has a very limited applications, right? Because of their high radiant intensity, EDLs are initially investigated for AFS, that is atomic fluorescence spectroscopy. So although the high intensity of EDLs are not needed for most atomic absorption spectroscopic applications, so for some elements, that is selenium, arsenic, and distrin, EDL exhibit better detection limits than the HCl, hollow cathode lamps. Okay, right? So this occurs because hollow cathode lamps for these elements are of low intensity or low stability. So this has a particular specific applications. Okay, so the EDL lamp is ideal for elements whose resonance lines are below 200 nanometer. And the third one is when the dissolved solid in the solution is high. So you have to select which burner for burning application. That is, first is the pre-mix burner, second is the total combustion burner, and you can say any burner can be used or burners are not used. You have to choose the right options among these. I'll wait for 1 or 2 minutes, and after that I'll explain. And if you are having idea, you can type in the chat box. Okay, the pre-mix burner. I got one answer. Okay, so here you can see the schematic for both the burners, that is premix and total combustion burners, right? So what the phenomena exactly happens in the premix burner? Okay, as it name indicates, premix means you are getting the pre-mixed fuel and auxiliary oxidant supply here, right? After that, the sample is mixed in a mixing chamber with this mixture and goes to finally goes to the burner head. But in a total combustion burner, it basically merges the function of nebulizer and a burner. So in this kind of burner, the suction created through the compressed oxidant streaming past the inner capillary introduces sample straight to the flame, right? Here you are getting a premix fuel and auxiliary oxidant supply. It is not that kind of thing in case of this complete total combustion burner, right? So if there are some suspended particles, okay, so let me explain. If there is a burner, this kind of thing, there are some holes here in a premix burner. So if a solution containing high solids are introduced here, what can happen? The solvent, or you can say the aqueous solution, get vaporized, and the solids can deposit here into the holes, right? Or that can clog these holes, that can make these tube very highly pressurized or may explode, right? But in the total combustion burner, there is no such kind of thing. Okay, you can see here in premix burner, laminar flow, controlled, uniform droplets, low turbulence, and less electrical noise, because you are getting everything premixed. But in case of total combustion burner, you are getting a high electro high electrical noise, so noisy flames, right? So in this case, in total combustion burner, entire sample is aspirated. Okay, so high solids can be handled by this technique. That is the total combustion burner. So on the basis of this discussion, we can say the total combustion burner is advantageous in case of high dissolved solid in the solution. Right? Clear? Okay. Right. The next one is in atomic absorption spectrometry, the high flame temperatures are obtained. Basically, you have to tell from which mixture or which combination of oxidant and fuel gas you can get the flame of high temperatures, very high temperatures. First option you are given air acetylene flame, oxygen acetylene flame, N2O and acetylene flame, or hydrogen air flame. Okay, so all the uh, flame temperatures and maximum burning velocity are tabulated here. If you take this combination, that is, if you use natural gas as a fuel gas and air as an oxidant gas, you will get this temperature in degree Celsius, right? That is 1700 to 1900, and this is the maximum burning velocity. Same, if you change the oxidant gas and fix the fuel gas, you will getting this range of temperature. And for this particular combination, you will getting this burning velocity, right? And similarly, if these two combinations are used with the fuel gas hydrogen, you will getting this kind of this range of temperature. But you can see in case of acetylene and oxygen, you are getting the maximum flame temperature. Okay, so you can just acetylene oxygen. This will be the right answer. Next is a very important and interesting question, that is, alkaline earth metals are determined by atomic absorption spectrometry in stoichiometric flames, slightly reducing flames, slightly oxidizing flames, or any flame types. Before trying to solve this question, you can just recall what are the properties of these alkaline earth metals. They can be easily oxidized, right? So try to answer. Okay, first I'll discuss about the different flames. Okay, so in this particular picture, you can say this one is the reducing flame and this is the oxidizing flame, that is bluish in color. Okay, so what happens, like if I draw the schematic here, this is hollow cathode lamp and this one is here the flame, right? If this is the radiation, okay, and if you there are three different reasons of this flame. First is primary combustion zone, secondary combustion zone, and interzonal region. So, if you have a metal of some specific property, like if you say this is the reducing agent, or this you can say the oxidizing agent, right? Or it can oxidize easily. Okay, so basically, you have to adjust the height of the burner according to the property of that element, right? So there is a certain range of height of the HCl that should pass through to get the maximum absorbance. And you have studied in the lectures also. There is something like point 0.2, point 0.5 to 2 centimeter height. You can adjust. Okay. So in atomic absorption, always give a small screw at the bottom of the nebulizer or burner so that you can increase the height of the burner to the desired level, right? So whenever you want to start a chemical analysis, your aim is to get maximum absorbance. Okay, and The other properties of alkali metals, they do not easily form the free atoms, but they also ionize to appreciable content at these temperatures, right? If they ionize, like say this phenomena is happening there, so this is the oxidation. So what you have to do for accurate analysis of that metal, you have to give it the reducing environment so that this oxidation or ionization can be restricted, right? So the same thing is written here. The atomic absorption for alkali metals like sodium, potassium, lithium, cesium, and all is not easy using atomic absorption because of this ionization problem, right? So due to this phenomena, they ionize and absorption signal is smaller than the emission signal. So what we have to do, because the alkaline earth metals, you know, the calcium, magnesium, etc., they are determined in a slightly reducing flame. Okay, so what it basically concludes, if I have to analyze calcium, so I have to adjust the burner height such that the calcium is getting the contact of the radiation in this region for better measurements. That is the uh, reducing flame, red flame, right? Because of this ionization can be restricted and the metal can be analyzed very efficiently. So the right option will be slightly reducing flames. Are you getting my point? If you are okay, just type yes. Okay, okay. Thanks. Let me go to the next one. That is the quartz tube is used in the analysis of AAS because it changes the direction of the flame, it increases the path length of the measurement, it is convenient and cost effective, or it gives higher temperature. I will wait for 1 or 2 minutes. If you can get the idea about the right option, you can convey it. Okay, so let me explain. So in theoretical classes, you have read this slide actually. So the an ingenious way of utilizing the height of the flame to achieve long light path and hence greatly improve sensitivity, that I was discussing something here. Okay, so what is another aim of the analyst, that is the analyte has to go to the longer path length, right? So the an ingenious way of utilizing the height of the flame to achieve long light path and hence greatly improved sensitivity is to direct the flame into a tube made of suitable heat resistant material such as quartz or ceramic. right? So the long tube technique is likely to be used for those metals which do not readily form oxides in the flame. The sensitivity of 10 to 100 times those obtainable in ordinary flame have been reported for this particular element, that is cadmium, zinc, and the noble metals, right? So basically, uh, quartz is only used for increasing the path length of the measurement. About if you want to discuss the more details, or if you want to read more details, you can see the elaborated lectures, right? The next one is, when using a HCl hollow cathode lamp as a source, the monochromator should have a spectral band pass of the order. These are four options: 2 nanometer, zero point 0.2 nanometer, 0.02 nanometer, and 4 nanometer. For better accuracy, you have to keep many points in your mind. That is the band width, spectral band pass, etc. Because let's say if you are giving a radiation of 397 nanometer to any metals, and if it is emitting, right, 397.2, okay, so the acceptable limit should be within zero point 0.2 nanometer, that is a spectral band pass. It should have a order of this, because why it is selected particularly. So this is the reason. These are the slit width. Okay, this is zero point 0.2 actually, right? You can see here, this portion is showing a very sharp peak, right? And also, this peak is showing a greater signal to noise ratio. Signal to noise ratio. That is, what does that mean? You are getting a higher signal compared to noise. That should be the first priority of any this type of curve. Like say, if you are discussing with chromatograph, right? If this is a peak, okay, so this peak should have a greater or appreciable signal to noise ratio. This one is the noise and this is the signal, right? So at this particular spectral band pass, that is zero point 0.2 nanometer, the signal to noise ratio is optimum. After this, it is getting decreased, and after decreasing the slit width, also the signal to noise ratio is decreasing. So this is the optimum value, right? So zero point 0.2 nanometer, the a monochromator should have a spectral band pass of this order, right? For better accuracy and measurement. The next one is, in a double beam AAS, the sample beam is modulated as at double the frequency of the reference beam. The sample beam is modulated at half the frequency of the reference beam. The sample and reference beam are modulated at high frequency. The reference beam is not modulated, right? If you are having any idea, you can just type in the chat box, or I will be discussing the modulation phenomena, and after that, I'll let you know that what should be the frequency of the sample beam and the reference beam, right? Okay. Okay, let me explain. So, in a typical instrument, it is necessary to eliminate interference caused by the emission of radiation by the flame. Right? The emitted radiation at wavelength outside of the monochromator band pass is of course removed by the monochromator. However, the emitted radiation corresponding in wavelength to the monochromator setting is inevitably present in the flame because of excitation and emission of analyte atoms and flame gas species. So, to eliminate the effects of flame emission, it is necessary to modulate the output of the source. Okay, what does that mean? Let if is hollow cathode lamp here, and this is a flame, right? And these are the vapors of metal atoms, right? So if there is a monochromator, it can mostly it can eliminate the, or it can control the broadening, or you can say the band pass, right? But after this, some flame can also emit the same frequency radiation, right? So that will be the interfering in nature, right? So the detector then receive two types of signal, an alternating one from the source and a continuous one from the flame, right? Because there will be other elements also except the element of analyte, interest, analyte of interest, right? So what it is basically describing, right? If you in a single beam AAS, there is no problem because there is only a single beam. But in the case of double beam, what technique is preferable, that this hollow cathode lamp radiation is splitted into two parts. One is getting the intensity without any sample introduction, and other one is with the after the interaction with sample, right? So if this is the frequency, sample beam is modulated at frequency f, right? And the reference beam is modulated at frequency of 2f, right? And after that, these two signals, or you can say two intensities, are combined at the exit slit of the monochromator, and multiplier output it feed to an amplifier. So this is the basic phenomenon. Okay, so what the modulation means, if there is absorbing analyte is present, okay, so these alternate band, the intensity of this, or you can say frequency, is getting reduced. That is 2f minus f, it will be just half of this 2f. Okay, and if there is a absence of absorbing light, you will getting the this continuous beam of 2f frequency, right? So in this way you can differentiate what which radiation is coming through the flame and which radiation is without the analyte, right? So what does the modulation is required. So you can see sample, in the case of sample the frequency is f, and in the reference it is 2f. So basically the sample beam is modulated at half the frequency of reference beam, because reference beam is put at 2f and it is f. So this one will be the right answer. Okay, right. So next question is about detector, the most standard detector, that is PMT. Photomultiplier tubes are preferably used as detector in AAS because there are four options. As usual, they exhibit good spectral response at all relevant wavelengths. They contribute little signal to noise ratio. They ensure good signal to noise ratio, and none of these. Okay, so basically you have to focus on the advantage of PMT. If you are having any idea, you can just tell me. Okay, let me explain. Before choosing the right option, I will introduce about PMT. So PMT is basically a detector, right? It is commonly used for measuring the intensity of UV and visible radiation, particularly. What it contains basically, this is the basic structure of PMT. It contains a large number of diodes, right, which amplifies basically the number of electrons. It basically increases the electron gains, right? If you are getting some incoming light, or you can consider is at a output from here, right? So it can increase the number of electrons, or you can say it can amplify the signal. Okay, so basically this is the definition. The measurement is based initially on the photoelectric effect and then on the amplification of the signal through a series of diodes. Okay, and initiation of detection process involves radiation striking the surface of a photoactive surface and disclosing electrons, right? If light is falling here, this surface should have a quality of it should be photoactive basically. So it should emit the electrons. So basically these are the secondary electrons, right? And if striking continues with time, the number of electrons, the number of electrons will get higher. So that is basically phenomena of PMT. Okay, so electron dislodged from this surface are accelerated toward the first diodes, and then which is at high voltage, and then striking goes continuously goes there. Okay, so there a cascade of electrons that produces a large current is produced. Okay, so PMT has a quality that it exhibit a good spectral response. In the if you are having about some infos, what is a good spectral response? It should have a good signal to. It should have a high signal to noise ratio, right? It should cover all the relevant wavelengths with minimum broadening, right? So the first one will be the right answer. And the last one is the hollow cathode lamp used for the determination of element provides higher throughput, better accuracy, convenience, and higher sophistication. Okay, and basically the HCl is used because it has higher throughput. It consumes less energy and can provide the high output. So the higher throughput is the important characteristic of the hollow cathode lamp. So this was all about the assignment 4. Uh, Thanks for attending this session. I'm leaving the call. Thanks a lot.